We are Group Sofa Potatoes, and this is our Huffman coding presentation. We have passed both RTL and gate level verification. The chosen clock period is 0.8 nanoseconds, with area, power, and simulation time provided. We have also done coding style check, but not yet code coverage. This is our algorithm. We start with initialization, then read and count data to build the simple frequencies. After that, we perform sorting using an even phase and odd phase, and we repeat until sort is done. Once sorting is ready, we merge the least two groups, then update the Huffman codes and the masks. We keep repeating the merge and sort until there's only one group left, and finally we output the results. This is the FSM control of the entire hardware. We start from S0 idle after reset, then we go to S1 read, and when count reaches 100, we enter the countdown stage and then the sorting stages. S3 and S4 sort even and sort odd. We loop between these sort stages until sort is done. Then we go to S5 merge. Each merge reduces the number of groups, and we repeat sort and merge while total groups is still greater than 2. When total groups equals 2, we go to S6 to output the final results. This is the block diagram of our hardware. The red arrows indicate the control signals of the finite state machine. At first, the counter's block receives the input data stream. During the read stage, it counts the frequencies of each symbol from count 1 to count 8. The counts are then stored into the group counts registers. In parallel, the group members block stores an 8-bit one-hot codes indicating which inputs belong to that group. Next, the odd-even sort block reorders the group counts and group members by their frequencies. Then design enters the merge state. The two smallest groups, min1 and min2, are selected. Their counts are combined using the adder and written back to min2. Their members are combined using an OR gate, then written back into min2. At the same time, the mask and Huffman codes blocks updates the codes during the merge section, respectively, through the gate logics. The total groups block checks how many groups remain. Each merge reduces the number of groups by 1, and repeats until only 2 groups remain, meaning the Huffman tree is complete. We evaluate the synthesized results across multiple clock periods. The highlighted configuration is our selected period with the best overall performance. Finally, here are the trade-offs using our odd-even sort algorithm. The pros are it's easy to implement, has a short critical path, and leads to small area. The cons are sorting requires multiple cycles, and the number of cycles can depend on the input pattern, and it can result in more power consumption compared to some alternative structures.
To solve the issue that odd-even sort may need more cycles and that the cycle count depends on the input pattern, we also introduce Bitonic sort as an alternative. The overall idea stays the same. We simply replace the odd-even sorting block with Bitonic sorting, and the merge process continues until the remaining groups are small enough to output the result. This slide shows the state transition diagram for the Bitonic-based design. The system mainly loops between stage 3 for sorting and stage 4 for merging. However, due to timing constraints, in the actual implementation, we stop the process when the total number of groups reaches 2 and directly output the results. In terms of hardware structure, the design is almost identically to the previous one. The only difference is that the odd-even sorter is replaced by a Bitonic sorter. From the synthesis results, we can clearly see that Bitonic sort has a fixed number of cycles regardless of the input pattern, which successfully solves the cycle variation problem of odd-even sort. We also observed that the best performance is achieved when the clock period is set to 1 nanosecond. However, although Bitonic sort requires fewer cycles, It also introduced a very large area in a long critical path, which hurts overall performance. So in the end, even though Bitonic sort is more predictable in timing, we choose odd even sort for our Huffman coding project because it offers much better area and delay efficiency.
This section is challenge encounter and waveform verification. The first problem we meet is the count error. From figure, we find that the count value is always that of the first one input data, which means the first one data isn't counted. This is because there's no state transition time between state idle and read, which means reset and grade valid input respectively. The solution is to postpone the time that data start to deliver to the circuit from a trial period of 3 to a trial period of 5. And this is done by the TA, and we get the correct waveform. The next problem we encounter is the sort error. Uh, from the figure, we find that the stage would always go to 5, which means the merge stage, even if the sort stage haven't down. This is because we use the even condition statement at the end of our sorting. This is our expectation. But what we indeed get is the even condition statement being used at the end of even sort. So it would always be correct and go to the merge stage. The solution is to modify the even condition statement into the odd condition statement. This and we get the correct waveform. The last problem we encounter is Huffman and master code error. From the figure, we notice that the Huffman coding is done with more one cycle. This is due to the ending condition statement. Uh, if we write the total group is equal to 1 or not, then the next stage have not changed to the end stage. If we write this type of ending condition statement. So we modify the ending condition statement to the total group is equal to 2 or not. Then the next stage will have enough time to change to the ending stage. So we get the correct waveform. And this part is coding highlight. Uh, this code is to ensure master next is always the right shift of mask and plus 1. So as to position a bit, we want to add by 1 or 0 when we do Huffman coding. The next is initialization. The most noticeable is one hot group member value. This variable helps us determine which Huffman code to be merged and do Huffman coding. So from the figure, we can notice that if the x of A2 is equal to 1, that means the group contains an A2. And this arterial code block is the key module of our Huffman coding algorithm. For loop and the group member is to search which input index Huffman code need to be plus 1 or 0. And then we use mask and mask next to position a bit. Give right child 1 at given bit by XOR gate and update mask. The value at given bit of leave child is not changed, so just ensure updating mask. After coding, we do merge plus 2 list child number and the member variable of 2 list child group do bitwise OR. The function ensure at the next stage the index of Huffman code will be fine. And this part is supplementary appendix. We have done the test bench with 3 pattern. This is a verification of sprite class. We have done a data lookup, horizon design, and hardware design coding. We still doing logic synthesis, circuit optimization, and we will start to write the final report. This is our work division table.